Ever wonder why some AI models learn faster or perform better than others? What if there was a way to help machines adapt during training, just like we do when faced with challenges? Today, we're diving into a groundbreaking technique called stress-aware learning, SAL, that's redefining how we train neural networks. Let's start with the basics. Traditional optimizers like Atom adjust model parameters to minimize loss, but they can get stuck in sharp areas of the loss landscape. Think of it like a ball rolling into a narrow valley. These spots might work well on training data, but fail to generalize. SAL solves this by adding a clever twist, a stress signal that monitors training difficulty in real time. Here's how it works. Imagine the stress signal as a built-in thermometer. Every epoch, it checks if the model is improving. If the loss and accuracy plateau, like a car stuck in traffic, the stress level rises. When it hits a threshold, SAL kicks in with two strategies. First, noise injection. It gently perturbs the model's weights, like adding a little shake to a wobbly table to help it stabilize. The more stress, the bigger the shake, encouraging the model to escape sharp minima. Second, if stress gets too high, SAL applies plastic deformation, a structural adjustment to the final layers of the network, similar to reshaping a bent wire to find a smoother path. But why does this work? Let's simplify the math. When SAL adds noise, it effectively smooths the loss landscape, pushing the model toward flatter, more robust solutions. And when it triggers plastic deformation, it's like giving the model a fresh start in the most critical areas, preventing it from getting stuck. In experiments, SAL outperformed traditional methods in both stable and unstable scenarios. On datasets like Imagenette, it achieved higher accuracy without overcomplicating things. Even when training conditions were messy, like with noisy data or unstable learning rates, SAL kept the model learning, adapting in real time. What's truly groundbreaking is how SAL avoids fixed rules. Instead of relying on preset schedules, it uses feedback loops to decide when and how to intervene. It's like having a personal trainer for your model, adjusting workouts based on how you're performing. Now, let's unpack what those stress-aware adjustments really mean. Think of SAL as a system that's not just reactive, but almost intuitive. When something starts to get too much, like a thermostat sensing a room is too hot, it kicks in to balance things out. But how does it know when to act? Here's the cool part. SAL uses real-time data to detect when a process, system, or even a biological function is under strain. Imagine a car's suspension system adjusting to rough roads. SAL does something similar, but at a molecular or algorithmic level. It's like having a built-in early warning system that whispers, "Hey, things are getting tight, let's tweak this before it breaks." The methodology. Scientists train SAL to recognize patterns of stress through massive datasets. Think of it as teaching a robot to spot when a machine is overheating, or when a cell is struggling to function. Then SAL's algorithms automatically adjust variables, like temperature, pressure, or resource allocation, to ease the load. And the results? Systems using SAL's stress-aware tweaks show remarkable resilience. They handle spikes in demand, environmental changes, or unexpected challenges without crashing. It's like giving a system a built-in reset button that works before problems escalate. So what does this mean for AI? SAL shows that adaptability is key. By mimicking how living systems respond to stress, we're building smarter, more resilient models. Whether you're a researcher or just curious about AI, this is a glimpse into the future of machine learning, where systems don't just learn, they evolve. Next time you see an AI model performing brilliantly, remember, behind the scenes, it might be using a little stress management to stay on track. Thanks for watching, stay curious, and let's keep exploring the wonders of AI together.